Hey guys, welcome back to another video. Today we'll be looking at a bit of differentiation when it comes to partial derivatives. We'll be dealing with both the first order as well as second order partial derivatives. So one of the first things you will notice when you have to differentiate something partially is the way in which the function tends to come. It has a special notation that looks as follows. It's read as f of xy, and then you have your routine equal sign because it's going to be an equation, and then your function can have variables such as follows: 3x squared, y squared, minus 2y. Okay, now the reason that this function has a special notation that does not look like what we are accustomed to is because usually when we have functions f of x, it's generally only in terms of the variable x. So what happens is that by extension, when you have functions that have multiple variables present, you will see that the function gives a count via use of that comma. All right, it gives a count of the fact that you have multiple variables present. Now, when you're differentiating something, let's just say we have y is equal to 3x squared. If you wanted to differentiate and find dy dx, you can easily apply your standard rules. You'll get 6x. Now, you can differentiate with respect to x in this case because our function is only written in terms of x. So what happens when we have a function as the one above and it's written in terms of multiple variables? What exactly do we do? This is where the term partial derivatives comes into play. You see, when you're trying to differentiate something, a function, right? Partially, so let's take note of that. Partial differentiation, DIFF for short, takes place when you have multiple variables. So you're seeing that you have multiple variables present. However, but what you need to do is hold only one variable. Whoops. Hold only one variable and keep the others as constants. That is the key word here. That is the key word on this screen. And I'm going to be speaking a lot about that word constant. Now, to be honest, it may not make full sense to you as yet what's written in purple. Like, what do you mean hold only one variable and keep the others as constants? Exactly. So of course it's math. Let's work by example. Okay, so what you see on screen is that we have a function and it's written in terms of two variables, x and y. Now, for this question, they want us to differentiate this function with respect to x. Now, interestingly enough, partial derivatives have a special notation. It does not look like a D, rather it looks like a sigma sign. For those of you who are doing physics, you'd notice that the symbol looks like this. And this is read as delta x, delta y. This is read as delta f, delta x. This is read as delta g, delta h. All right? So I'm just giving you guys a look at the notation when it comes to partial derivatives. It's not the standardized dx or dy that you would typically see. All right, and take note that letters Okay, when it comes to letters, they're just arbitrary. So standardized, yes, when you're differentiating, you have the y on the numerator and you have the x on the denominator. When it comes to functions, your function can be any letter. It does not have to be x. It does not have to be the f. It can be h, g, it can be any letter pretty much. And then the variables associated with that function can vary as well. So it's very important when you're differentiating something partially that you consider all of the letters involved in your question. So in this question, we can see that our function is called f. So therefore, some of the things we can find is that we can differentiate this function f with respect to the variable x. Now take note, we do have two different variables present. That means we can also differentiate this function with respect to y. Those are two of the first order types of partial derivatives that you can actually find when it comes to differentiating a function partially. So let's go ahead and let me show you what it means to hold a variable constant and how we can actually differentiate a function with respect to only one variable. Alright, so the first thing I'm going to show you guys how to do is how to differentiate this function f with respect to x. Step 1, use the correct notation. You'll notice immediately on screen that we actually have that sigma notation I was telling you guys about. So you can see it top and bottom. The name of our function is f, so we will represent that sigma f, delta f, however you want to describe it on the numerator. And our intention is to differentiate this function with respect to x only. So what we're going to do is that we're going to set every other variable, which is y in this case, as a constant. What happens when you set things to become constants? Well, basic differentiation rules says that if you have numbers like 5, -1, 2, a half, doesn't matter, once it's a constant, then the derivative of constants is 0. So if you consider that y, the variable y in this question, is just a number or a constant, remember when you're differentiating, essentially you tend to put the numbers in front. So we are going to actually highlight all of our constants on that right-hand side of the equation there. So it will be easier when it's time to differentiate partially. So let's go. Now, if you had to differentiate x cubed, where x is considered a variable, that value is simply 3x to the power of 2. Next up, it's very, very easy to observe 3x squared y squared as a product of two separate functions. But when we're doing partial derivatives, you have to train your mind to understand and see that if you're differentiating with respect to x, y is just a number. It's a constant. So what we do is, first up, I like to bring all of my constants to the front. When I'm finished, I like to highlight the only variables present that can actually be differentiated. Now that's actually not a product if 3y squared is considered to be just a number. In essence, you can think of this as being like the number 15, and then you have 15x squared to differentiate. You wouldn't use a product rule to differentiate that now, would you? So pretty much the same basic principles apply. When you're setting a variable as a constant, you bring it to the front next to the rest of the constants, and you go ahead and you differentiate what can actually be differentiated. X squared can be differentiated to get 2x. Similarly, as we move on further down, like I said, y is supposed to be a number. And if that were a number 3, 3 2's are 6. And the derivative of any constant is 0. So if you had to differentiate that third term present in that function, that last term just goes to 0. And we have no value here. Some students like to write in plus 0. There's no need for that. You can leave it out. In time, you will understand how to naturally generate your answers and how to naturally see certain variables as being just numbers. For now, we'll take it one step at a time. After differentiating partially, what you simply do is go ahead and we simplify what we have on screen. 3 2's are 6. Personally, I like to write my letters in alphabetical order, and that is our final answer. So this is how you differentiate a function partially. You consider the variable that you are differentiating with respect to on the denominator. You only differentiate that variable throughout your right-hand side while keeping the other variable constant. Let's observe what will happen if we were to find the differential of this same function, but instead with respect to y. Okay, so if we want to differentiate this function now with respect to y, we have to change that denominator to delta y. And we're going to go ahead and we're going to set the other variable present, which is x, as a constant. I'm going to highlight it so that my eyes can see it as just being a number. I'm going to underline all of my constants present in my question. And the ones in green are the ones that are differentiable. You can use color coding if it helps. So x cubed, if that's just a number, if we're setting that to be a constant, then the derivative of that is just simply 0. Moving on to the second term, I'm going to write down all of my constants present because I do have a differentiable variable next to it. Next, what I'm going to do is simply differentiate my y squared. That's going to be 2y with respect to y. Next up, I can see that I have a differentiable variable present as well in my third term, which is 2y. And when you're differentiating terms where you have the power of 1 being present in a variable, it's just simply the constant in front. So the derivative of negative 2y with respect to y is simply negative 2. So it's pretty much basic differentiation you perform. You just have to really train your eyes to set one of those variables as a constant. Next up, we're going to clean up this. So 3 2's are 6. We have x squared y minus 2. And that's your final answer. And I just want you guys to know that when you're differentiating a function with respect to x or y, you're going to get different solutions. The answers are not the same, unless it's a coinkydink. Alright guys, so stay tuned. Up next, we're going to build a little bit more into using these first order partial derivatives, and we're gearing up to get into those second order partial derivatives. Okay, I also wanted to show you guys some of the notations you will see in textbooks, YouTube videos, used by your lessons teachers, by your subject teachers, by your tutors, whoever or whatever you're looking at to learn. They may be using some basic standardized notation. So let's just say we have a given function f in terms of x and y. So typically you'll usually get a function f in terms of x and y. Then you can find several partial derivatives from this. For example, you can find the partial derivatives delta f with respect to delta x. Sometimes you can see this written as follows instead. You can have delta x of, and then they'll write the entire function as was given in square brackets. This one is seen more highly likely in textbooks rather than written solutions because it's a longer notation. Also, another way they can write this is by having a subscript. Here's the function f, and if they wanted to differentiate it with respect to x, they just write a little subscript. And then after, they continue to follow up with the variables present in that function. All right, so just take note of the possible ways you can have the notation set. Let me show you guys another one. If they had to have delta f, delta y, then you can have delta, delta y, and then of course you have your function. Or to show them, you can use a subscript. Hey, I'm differentiating f with respect to y, and that function has two variables, x and y. Okay guys, so just a short note on the way symbols can come across and confuse you, and if in exams you see any of these notations, now you understand what they mean. But the most popularly used ones are the ones to the far left. Alright guys, so pretty much that's about it. I think I'm going to head into second order partial derivatives, and via that second order partial derivatives, you will also have another chance to understand first order partial differentiation, because in order to do second order, you must perform first order at the beginning. All right, so stay tuned. Okay, so you guys just learned that some of the things you can find when it comes to partial differentiation is that you can have delta. Let me change the color on this. You can find delta f with respect to delta x, and that has a notation. You can see it in textbooks as f subscript x, and in terms of the function in terms of x and y. Sometimes instead of that, you may also see it, but very, very rarely, as follows. We're going to not learn that type of notation though. We're going to stick to this one. Now, another thing you can also find that we talked about is you can find... Okay, lost of train of thought there because there was a huge, massive power supply cut. So, gotta get my bearings back. Where was I? Okay, so we were talking about differentiating a function partially and its notation if you're differentiating it with respect to x. So pretty much this is what the notation would look like. If you wanted to differentiate it with respect to y. All right, so we went through this just previously. It looks like that. And you can write it as follows as well. Now, by extension, some other things you can actually find are something we would term second partial derivatives. And second partial derivatives are very similar to d2y dx squared type of differentiation. It's kind of like, you know, when you find dy dx when you're differentiating, and if you differentiate that a second time with respect to x, you would get d2y dx squared. Well, that same principle applies when you're trying to differentiate something partially. It's just that because we have multiple variables we can set constant, we actually have 4 possible second types of partial order derivatives that I'm going to show you guys on screen. So one of the first types you can have is if you choose to differentiate your function with respect to x after you differentiated it with respect to x the first time, what you end up getting is d2f dx squared. Delta, sorry. Next up, you can have a situation where you differentiate your function with respect to x. Again, that's the second differential, but initially you had found delta f delta y. Now, what is that going to look like? Well, it's called delta 2f delta x delta y. Next up, the two reverse situations can happen. And that's if, let's just say you differentiate your function with respect to y the second time, but initially you had differentiated your function with respect to x. That looks like delta 2f delta y delta x. You can see it looks like a switcheroo of the previous one we did in purple over there. And finally, you can decide to differentiate with respect to y if in the first instance you had also differentiated with respect to y. That would result in delta 2f delta y squared. So those are the four different types of second partial derivatives that you can actually be asked to find in exams. And I just want to point out these two. They do look very similar. Delta 2f, delta y, delta x, and delta 2f, delta x, delta y. And I just want to say that these two types of partial derivatives are actually equal. They usually work out to be equal once, if and only if your function f in terms of x and y happens to be continuous, if it's a continuous function. All right, so a bit of lower six knowledge there. And also if all of their partial derivatives are also continuous. So if the function and the derivatives are continuous, then these are set to produce the same value. All right, guys. So that's your notation on screen. Let's actually get into doing this question we have, and let's find all four second partial derivatives. Okay, so let's get into it. All right, guys, so you gotta hang tough with me, okay? This topic can get very, very scary sometimes. You gotta learn to train your mind and train your eyes to set variables as constants. So first up, we're gonna find the first order partial derivatives. So we have our first order derivatives, right, for short. And those are the following. I'm sorry, but my internet is just like running so slow. So we have our function. And what if we choose to differentiate with respect to x first? So we're going to set y as our constants. So I'm going to highlight all of my constants present. So we have 4y squared and y squared, that's constants. So now my mind tells me what is a variable. My eyes have help from underlining those details. So I can differentiate x squared to get 2x. And because that middle term has a variable present, x, I am going to pull all of my constants to the front. The only differentiable thing we have is x. And if you're differentiating something x, it's just the coefficient in front of x, which in this case would be 4y squared. So that's the differential there. And then for that last term, if you differentiate negative y squared with respect to x, that's 0, because y squared is considered to be just a number, just a constant. All right, guys, hope you really understand that middle one. Let me take this to the side. If you have 4y squared x, where this is considered to be like the number 5, then it's like 5x. And if you differentiate 5x, you'll just get 5. So therefore, that's why that middle differential, I just have a 4y squared. I hope you really can see it. Okay, take some time to get used to. All right, and that's your final answer. Isn't first order differentials actually easier than you thought? Now we're actually going to get into, let's do this one on this side. Let's go ahead and let's get the delta f with respect to delta y on this side. So now what we're going to do is we're going to consider the ones in red as constant. So the letter x is now our constant because we're differentiating with respect to y now. And if x is a constant, that means x squared is also a constant. So if I differentiate that, I'll get 0. My second term, my variables present are y. So I'm going to put all of my constants in front. That would be the 4x. And the derivative of y squared with respect to y is simply 2y. My last term can be differentiated easily with respect to y to also get 2y. My final answer, I can just multiply that 4 by 2 and get 8xy. So I'm going to clean it up in the same spot. 8xy minus 2y. And that's it. Those are your first order derivatives. Now let's move into second order. Okay, so second order happens when you have to differentiate your first orders a second time. Okay, so the first one you can get is to differentiate with respect to x, that delta f delta x. Now, how do you go ahead and get this done? This is going to produce delta 2f delta x squared. Well, if you're differentiating something and that something has been previously worked out, you can just write it in your brackets as follows. So I have just simply replaced this with its value. And you can see that we are differentiating this with respect to x. So we're going to set that y as a constant. And then 4 is also a constant. So that second term, the entire value after differentiating, will turn out to be 0. So the derivative of this would just simply be 2 with respect to x. Everything else goes to 0. When it comes to partial derivatives, answers tend to get more simplified. If there was something like third order, fourth order, fifth order derivatives, I think generally the answers will become so small they just go to 0. Alright, so let's go ahead and find another one. What if you had to find delta y of this function, delta f delta x? How are we going to do that? Well, first up, what's it going to produce? That's going to produce delta 2f delta y delta x. Alright, so how do we know what goes where? Well, first of all, according to our brackets, we have to find out what delta f delta x is equal to. Well, that's just 2x plus 4y squared. Once we have figured out what we're differentiating, we have to figure out what we're differentiating with respect to. We're differentiating with respect to y, so I'm going to underline all of my constants here. Oops. Our constants would be x. Alright, so our constants is 2 and x and 4. Next up, if you're differentiating with respect to y, everything is also a variable. So 2x is just a constant, The derivative of that goes to 0. 4 is the coefficient in front there, so let's write that in. And then if you differentiate y squared, you'll simply get 2y. Multiply, and your final answer is simply 8y. Now, this function is a continuous function, so typically if we had to find the reverse, we should get the same answer. And I'm actually going to work out delta x of delta f delta y up next so I can show you guys that. This would produce delta 2f delta x delta y in that order. And how do we work that out? Simply replace what we have in brackets. So what is delta f delta y? Well, it worked out to be, we have 8xy, let's write that, 8xy minus 2y. And what are we differentiating this with respect to? X. So x is our variable. So let me underline all of our constants. 8 is a constant, y is a constant, 2 is a constant, y is a constant. So immediately you can see that if you're differentiating with respect to x, that first term, your constants 8 and y go in front, and x is just a lone variable to the power of 1. So the differential of that is just its coefficient. And the second term is in terms of y and 2, which are all constants. So the derivative of that goes to 0. And you can see here and here that because the function in terms of x and y and its derivatives are continuous, that you get the results to be the same. All right, so that helps a lot of the time. Sometimes when they're asking questions like, are these functions continuous? It'll be easy to identify that those will never be the same values. Okay, and then finally, we can find delta. Let me work this in blue. Keep the color code steady. What if we were to find delta y of delta f delta y? That's going to produce delta 2f delta y squared. What is that? Well, it just means to differentiate with respect to y, this thingy in bracket. We have to find that. That was 8xy minus 2y. And simply, we're differentiating with respect to y. So 8 is a constant, x is a constant, 2 is a constant. And if we're differentiating with respect to y, that first term, 8x gets pulled out because that's a coefficient of y. And then the second term, if we're differentiating with respect to y, is simply negative 2. And that's it. Those are the 4 second order, 1, 2, 3, 4 possible types of second order differentials that can possibly come. Take note that the notation tends to look different. We have sometimes, let me show you one more notation that is possible for these. If we're differentiating a function with respect to x twice, you can have f sub xx. If you differentiate a function with respect to y, and then you differentiate it with respect to x, then you would have f of yx. Hold on. All right, so we have x here first and then y. Now you may be asking why I have the x first and then the y. That's because what's in brackets, that's the first derivative. Remember, you differentiate your bracket first. So essentially, we're differentiating the function with respect to x first. That's why x comes first, okay? Similarly, in this one, what's in bracket is what we differentiate first, and then our second derivative is what's outside brackets. Secondly, we differentiate it with respect to x. And then lastly, this one is easy. You differentiate with respect to y twice. All right, several different functionality notations. You have many more, and it's all good to understand how they can come. So in the event that they pop up, you know exactly what they want you to find. But generally, the most popular ones for your CAPE exam are these. So make sure definitively you guys really understand the notation form and how to train your eyes and your mind to see certain variables as constants. Okay guys, so that's about it for first and order second derivatives in terms of the lesson. If you would like to see full tutorial sessions on these questions, I have all of the past papers in a tutorial on my channel. Just go ahead and search for differentiation and you would find partial differentiation located in there. Tons and tons of examples and questions. Okay guys, so it was good to be with you. All the best and stay tuned. I will be releasing the implicit differentiation soon. Bye.